All right. So I have been arguing this projection trick. It is not discussed so much in the context of neural networks, but it has been a huge argument before neural networks, namely in kernel regression methods, kernel regression, also known as Gaussian process. So before neural networks became absolutely, the blockbuster, if you were Bayesian and if you still wanted to do something, nonlinear, you were using Gaussian processes. And they implicitly used this projection trick, and it was made very explicit. So for 20 years, the community was talking about support vector machines, and support vector machines do this very explicitly, this nonlinear projection to a higher dimension. And in this higher dimension, the problem then becomes simpler. Yeah? So in this high dimensional space, you can then use a linear classifier, or if you're talking about regression, just a hyperplane. And if you then project back to the original space, you get a highly nonlinear decision boundary or a highly nonlinear fit to your data if you're regressing. So that was the projection trick. Width is good. And the reason this is not discussed all that much these days is because if we have a neural network which has few layers, but many perceptrons in these layers, this would be called a shallow network. Yeah? And so these are also sometimes called shallow classifiers. And width is good, but what people have come to realize since is that depth is better. Okay, and now we come to the only experimental part of this lecture, of the whole winter semester, I'm afraid. So I created for you a two-dimensional feature space and set of labels. And I mean, a linear decision boundary is not going to cut it. We've just learned that if I create as many decision planes here as I have points, I will be able to do it even with a shallow network. But I am now going to invoke the construction of Montúfar and colleagues, okay? And the construction of Montúfar and colleagues is to say, I'm going to use as nonlinearity the absolute value function. Yeah, so as nonlinearity, this time we are going to use the absolute value of x. And so if I put, for example, along the first, if I put my origin here, let's say, and if I use the absolute value along the horizontal axis, then the negative values are going to become positive. So I'm going to fold along this axis here. And then, so let's say now my origin is here, yeah, at this point. And now I do the same. I apply the absolute value along my second axis. And that means I'm going to fold and the negative values are going to become positive. All right, and now I'm iterating this. Yeah? So I'm again using the my origin now is here. I'm again taking the absolute value, but if I did it right from this position, nothing would change. Yeah? So if I put my origin here, then I already have no negative values on the horizontal axis. So I need a bit of a bias. Yeah? So I will apply my absolute value function around a perceptron. I'm putting it here. And using this absolute value function, so I'm again folding, and I'm again folding along the other axis now, using the absolute value function. And I end up finally with this, okay? Now comes the final perceptron. I hope I don't hurt myself. So I'm now going to, or maybe I'm going to poke holes. So I'm now, you see, I'm now going to use a perceptron here in this space that we have constructed. And this is going to be slightly ornamental. I mean, we're, you know, coming closer to Christmas here. All right, here's my decision boundary. I hope you can see it dotted. And now let's see what this did in the original space. It classified my samples almost perfectly. I mean, I have one mistake here, but other than that, pretty good. Yeah, so with my decision boundary, I could have made an extra hole to say, you know, what is what side, because on my normal, I always put a normal vector to say in which way is it actually, you know, where's the positive class. So let's put another big hole, let's punch another big hole here to say that this is the red class. And I'm again, you know, unfolding just to make the point. All right. So now we have, in terms of this hole, a labeling of where is the red class and where is the blue class. And yeah, so now I have, in my original input space, a pretty complex decision boundary. And I have not needed many perceptrons for this. Yeah? So let's use this Montúfar construction on this toy example here. So this is we start with a two-dimensional input space, and I was folding along the horizontal axis. Yeah, so I could put a summation here, but it did not receive any input from the second axis at all. Yeah, so I could also omit the summation here. But in any case, we use the absolute value as a nonlinearity. So we were folding horizontally, and we were folding vertically, and then so folding horizontally, folding vertically. This is now our first latent space, yeah, with dimensions Z1 and Z2. And then we were doing the same thing again. Yeah? So again, folding horizontally, a summation unit which does nothing. But I do need the bias to, at least the second time round, to shift where exactly I am folding. So here it is not superfluous, the summation. And again, I put the absolute nonlinearity. And then, so I've done it once, we've done it twice, and then at the end came the decision boundary. Okay, and a label prediction. Okay, so this is what our network does, and then we can look at this decision boundary in the original space. That's what we did here, and we saw that it was actually, you know, a pretty complicated thing. So, in fact, I have now in my input space, I have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, depending on how I count. Okay, I'm not doing the exact numbers, but I have relatively complex decision boundaries in the input space with a relatively small number of perceptrons, and in particular, very simple structure of the weights, yeah, because here each perceptron acted on just a single axis. And now this is the toy example they provide in the paper, and then they do a bit of math also. But the intuition really is that the maximum number of regions that we define in the input space the number of regions or polytopes which a multilayer perceptron induces in the input space it grows polynomially in the width of the neural network. So by width, we mean how many perceptrons are there in one layer. But here, the sequence of perceptrons, those are called layers. This is, the first, or the input layer. This is the first hidden layer, and so on. And this maximum number of regions, it grows polynomially in the width, but it grows exponentially in the depth of a multilayer perceptron. So, in other words, we can represent a complex decision boundary or a complex nonlinear fit more compactly, so using less perceptrons, using fewer parameters, when using deep architectures. Now there is a price to pay for this, namely the things become harder to train. So if I change the way I poke my holes here, so what this single perceptron at the end does, how exactly its normal vector looks like, will have dramatic consequences across the entire input space. And the consequences will be a function of, so changing the parameters on this one will very much change the tessellation of the input space. But how it changes it depends on these other ones. Yeah? And this makes it tricky to optimize all of them jointly. And that means we need a lot of stochastic gradient descent iterations. And this is, I think, why in the early days of neural network, MLPs were shallow, because you could, train them reasonably with maybe 1,000 iterations or so. And nowadays, we run millions and millions of iterations to train these deep networks. So yes, they are more compact representations of complex boundaries, but they are more difficult to parameterize. All right. So I come to my summary already. we can combine, and by combine, I mean, compose sequentially. Okay, I'll say something here to create. Okay, I'm going to delete this word linear here because what I meant here by linear was to say that the perceptron has somewhere in it this W transpose X, but if I only if I did not use a nonlinear activation function, then, if a single perceptron does this, then a whole layer of linear perceptrons does that. And if I now apply, so let's say these are the weights from the first layer, and if I now apply the weights of a second linear layer to it, then this is just going to correspond to an overall linear layer, where this matrix A here is the product of W1 and W2, just the matrix product. So these nonlinearities are really of the essence. So we can combine multiple, maybe I should say simple perceptrons to create complex nonlinear models. But the nonlinearity matters. So it matters in principle, because without it, I don't profit from this projection trick, and I don't profit from this repeated folding of space. And it matters in practice, as you have remarked, because if I do use a step function as activation function, it is, easy to understand conceptually, but it would be a terrible choice to train. So we are going to discuss better numerical choices next time. And I was motivating perceptrons through the perspective of logistic regression, but the hidden layer activation functions need not be logistic sigmoids. And this is a mistaken belief that held neural network training back for a long time, I would say, in practical terms, because when people started building these deeper networks in the 80s and 90s, once they had understood logistic regression, they were quite happy to use this kind of activation function inside the network. But it impedes gradient flow. And so when people then reverted to rectifying linear units, this made a huge, this made for dramatic speedouts. However, in the final layer, it does make sense to use these logistic sigmoids. So for classification neural networks or MLPs, one should use logistic sigmoids in the final layer to produce numbers that you can interpret as posterior probabilities for the respective classes. But for regression neural networks, of course, this does not make sense. There, it makes sense to have a linear final layer. I'm mentioning it because it's a frequent mistake. If you do use a logistic sigmoid, then of course you're going to squash your output to lie in the simplex. So no single, or every single dimension of the output will be between 0 and 1. But if you model, with regression, something, then those values are not necessarily between 0 and 1. Yeah? So you want to use something like a linear layer in the end. Okay, and for a given number of parameters, deep neural network have more flexibility or have more capacity than shallow ones. Very good. Then we will continue from here for quite a few weeks with the study of neural networks, in particular going to more advanced or more specialized, both more specialized and more advanced architectures to let you work on real-world problems. Have a good time.